In the video on routing protocols, I made the assumption that viewers were familiar with the Dijkstra algorithm and the Bellman-Ford algorithm. However, I also promised to cover those two algorithms in two short videos. This is the first of those two videos. It discusses the Dijkstra algorithm and it explores it by working through an example. The idea is that viewers who watch me working through the example should be able to use the algorithm and understand its functionality. However, those who are more interested in the topic are advised to read the original paper on the topic and get a more formal introduction to it. The Dijkstra algorithm determines the shortest path or the cheapest path through a graph. In the language of graph theory, the Dijkstra algorithm assumes that one has a graph. The graph is fully known, so one has a bird's eye view of it. And the graph consists, like any other graph, of vertices and edges. The edges have costs associated with them. Every edge has its own cost associated with it. And the idea then is to find a path from the origin vertex to every other vertex in the graph such that the cost of reaching that destination vertex is the lowest when one adds up the cost associated with the edges one has to traverse. Or in terms of a network, it is exactly the same question. One sits with a network where nodes are linked by various links. Every link has a cost associated with it. Note that this cost, as we've said on a couple of occasions, is not necessarily a monetary cost. It may be that it is a very slow link and you want to avoid it and therefore it has a high cost. Or there may be some other reason for assigning these costs. The point, however, is that every link has an associated cost, and then one wants to find a path or a route via this network from this given starting node to every other node in the network. And the cost, when one adds up the cost of all the links that are traversed to reach the destination node, must be a minimum. And that's exactly what Dijkstra is used for in the world of networking. It determines routes so that those routes can then later on be used by packets that are flowing on layer 3, where they are routing or forwarded from one router to the next. Let's look at our example and see exactly how the Dijkstra algorithm works. Dijkstra's algorithm is an algorithm that determines the best or optimal routes from a given node in a network. This network or this graph is known, so there's a global perspective of what is to be mapped, and it proceeds from this starting point, the origin node as indicated on the screen at the moment, and then it keeps on adding nodes, and the nodes that it adds are part of the known network and they will not change for any reason. However, as we add more and more known nodes, the neighbors of those nodes become candidate nodes and we will add the cheapest one of them. Dijkstra's algorithm is greedy in the sense that it picks the best option out of the available options, and it manages to do that and still get the best global solution. Also displayed on the screen at the moment are the other nodes that we know exist on the network, since we have this global view of the network or of the graph, but we have not really reached their neighbors yet, so we do not have any idea how to get to them. We're going to illustrate what is to happen here by following an example. And for this example, we will assume that we have the graph that is shown right now. It consists of 6 nodes. Those nodes are labeled A through F, and the edges are shown, or then the links between the nodes, and the costs associated with any of the edges is shown next to the edge. We will start from a given point in the network. So we will start in this example and work through it from A, and that will determine all the best paths from A. However, we could also start from B and C and so on. And in fact, that is what one will do if you want to determine all the best routes from given starting points, from different starting points. Just to make this point clear, if we start from A, then we will never work a route out to reach A. Hence, what we are doing will not be beneficial for the other nodes because they need to be able to send a message to A. So what we're going to do is select our node where we start, and as noted for this example, it will be A. The algorithm proceeds by looking at the neighbors of the node that we are currently focusing on. So since we are focusing on A, it means the neighbors are B and F. And since B and F are neighbors, they are added to the candidate set. In the picture on the screen, the candidates are shown in green, so B and F have just become candidates. Since we know that the cost to reach A is 0, it means we can determine the cost to follow the entire path to B and F, since both of them are only a single link away, a single hop away, and that gives us a cost of 1, a total path cost of 1 to reach B, and a total path cost of 5 to reach F. Dijkstra, as we noted earlier, is a greedy algorithm. So what we will do is we will pick the cheaper of the two, or in general we will pick the cheapest, the lowest cost available nodes, or the lowest cost candidate nodes. There you can also see that we have changed our A to a blue color. The blue color are those that are already in the network. And at this stage, A is the only node in the network, and we have a choice amongst B and F. B at a cost of 1, F at a cost of 5. So obviously B is the one that is chosen. It is the cheaper of the two. And now we're going to proceed in this same fashion. And in each case, we're going to look at the neighbors of the node that is the focus. And to look at the neighbors of B, we draw a little line around it when we depict it graphically. So the neighbors of B are, as is obvious, A, F, and C. However, what we want to do now is to add C, first of all, as a candidate, because C thus far has been unreachable, but F also becomes a candidate in a slightly different way. So if we indicate that, you will see that at this point, the total cost to reach B is 1. That's already indicated in blue. That will never change. One is to add 1 to B to get to C, and the candidate option F is at a cost of 9 because it's 1 plus 8. However, here in this corner, we are running into a potential problem because there we can see F now is a candidate with 2 costs. And Dijkstra being a greedy algorithm, we will always pick the cheapest one, so there is no reason to pick it at a cost of 9. So what this means is the fact that we've learned that F is a neighbor of B is useless. We have to discard that option because it only leads to a higher candidate cost of F, and we discard that neighbor and we are left with only A and C as neighbors. But as we noted earlier, A cannot be a candidate because it's already been chosen, it's already in the known set. So C is the only candidate that now becomes available. So let's move on and forget about the neighborhood of B. B has been selected. It is a part of the known network along with A. And as you can see in green, we have two candidates. And the candidate F comes at a cost of 5, and candidate C comes at a cost of 2. Again, being greedy, we pick 2, the cheaper of the two. C becomes the next focus of extending our network. As we do in all of these cases, we look at the neighbors of C, and the neighbors of C happen to be B, E, and D. We already said that the fact that we see B as a neighbor is useless because B cannot become a candidate. But just for the sake of illustration, let's consider all of these candidates, and you can see that D is now a candidate. The total cost to reach C was 2, so 1 further means the cost of D is 3. Total cost to reach C was 2, so a cost of 3 means E is a candidate at a cost of 5. But if we were to try this and say, let's go to B, then it would be 2 plus a cost of 1, a cost of 3. But that is already much more than the cost of B was. The cost of B was only 1. So clearly we're not going to ever pick this. So as we said earlier already, it simply doesn't make sense to go back to nodes that are already in the network. So that one should not be there, and we should only look at these two candidates that have been added, at the very least, while we are considering the neighborhood of C. But we can now stand back. C has been selected. It was the cheapest one, and it led to the addition of these two nodes. However, we have 3 candidates to select from. One at a cost of 3, one at a cost of 5, and another one at a cost of 5. With those 3, clearly D is the cheaper one, and D is the one to which we turn our attention. It is now part of the network, but to emphasize that we want to look at its neighborhood, we have it indicated as a star there, and we draw our boundary around the neighbors of D. So there's D, and the one neighbor happens to be C. C is already part of the network, so that is useless. But E is a neighbor, and yes, it's already a candidate, but who knows, we may have found a cheaper cost for it. So let's add that line to see how much it costs. Now do keep in mind that there was a cost of 3 to reach D. An additional cost of 2 means the total cost using this new path to it leads to a cost of 5. Now this is clearly a problem, because the algorithm says we should pick the cheaper of the two. What has in fact happened here is that we've discovered a new path to E, a new link to E, but it didn't improve on our knowledge at all. Didn't improve on our knowledge at all in the sense that we already knew that we could reach E at a cost of 5. And therefore, this new knowledge that we can, using the link between D and E, also reach E at a cost of 5, that's useless. So being useless, we're going to discard useless information, and that no longer is a link that we consider to be an option, and it just becomes a plain old link not to be used. At this point, we have 2 candidates in the network left, and again we have to pick the cheaper of the 2. And here we are running in a similar problem. Usually one of the 2, if you have to make a choice of one of the 3 or one of the n, will be cheaper. But Once in a while you end up with this sort of situation where the costs are exactly equal. And in such a case, it does not matter which one you pick. I can pick E or I can pick F. Let's pick F. So F becomes the focus of our attention, and what we should do, as always now, is to look at the neighbors of F. So if we draw our boundaries in, the neighbors are E, B, and A. A and B are useless because they are already part of a network. We won't discover anything cheaper going to them. But we may discover a cheaper path going to E. The cost to reach F was 5. This link costs 2. So the total cost following this new discovery is 7. Unfortunately, it's useless information since we already can reach E at a cost of 5. So what we've discovered is a more expensive option to reach E. That means it's useless knowledge, we discard it, and that's of no use. What we do finally is we can remove our boundary, and we have F as part of our network that's been selected. Now we have only one candidate that remains, E. So by definition, it is the cheapest one. It does become the focus of our attention. To take it further is a bit ridiculous, but for the sake of this example, let's do that and draw the boundary around E and its neighbors. So D, C, and F, obviously they are all part of the network already, so they cannot become candidates. In fact, everything in this network is now part of our known network, and we cannot go any further. Suppose that we have performed this calculation, and the question then is, what are the various routes that we've discovered? The path from A to B is that path at a cost of 1. The path from A to C is that one at a cost of 2. The path from A to D is that one at a cost of 3. The path from A to E is that one at a cost of 5. And the path from A to F is that one at a cost of 5. The question is now, how does one implement the algorithm given the fact that the way in which we've presented it used pictures extensively, and pictures are not always easy to manipulate, not that sort of graph at least, while writing computer code. So what we will do is to use something that looks like a tabular approach. Actually, what occurs here is that every line will indicate the values that we compute at every subsequent step. So we're not really completing a table as such. We are rather just iteratively working through the process and then adding one additional line of values in each case, and that overrides the previous line of outputs. So it's one single set of data values that we manipulate. The values that we are going to manipulate are displayed on the screen right now. It consists of a row number, that's simply the iteration number, how many steps are we into the algorithm. Then we have S, our set of completed nodes. In other words, the set of nodes that have been added to the graph that we know how to reach. They are already part of a path, and there is no point in looking at them again. Then we have the candidate nodes. Those are the ones that we colored in green. They are neighbors of the set of nodes that we know how to reach. So we also know how to reach the candidate nodes, but we will in each case from the available candidates only select one, and that will be the cheapest one to get to. That will be added to the set. That will generate new candidates because it may bring in new neighbors, and then we will reconsider the candidates available at that point. And then we will, in each case, as we said a moment ago, select the cheapest alternative that is available, the cheapest candidate that is available. In these major columns, we will store the total cost to reach B, C, D, E, and F from A to the best of our knowledge at this point in our calculation. So initially there may be some nodes where we don't even know how to get to them, and there will be no cost associated with them, but over time we will be able to reach them and we will have a cost, but that cost may decrease up to the point where we add that node to S, and that will never change again. This prior column is one that says who will be the final node on the path that will deliver to B, or on the path that will deliver to C, on the path that will deliver to D, or to E, or to F. So it's the immediately preceding one that will go into those columns. To make it practical, let's start with the processing. So here we have our table. It is basically empty. In a rather tiny font, we have the node that is known to be reachable at this point, and that happens to be A. And we've used a tiny font here because the set will grow and we will keep track of that set in a rather visual manner in any way. At this stage, there are no candidates, so we cannot make any selection, and we simply have to look at our network, at our graph, in order to determine which nodes are candidates. And obviously, the candidates will be the neighbors of the node that we've just introduced, namely A. So going back to our earlier picture, we realized that A had two neighbors, namely B and F. So A can send something directly to B at a cost of 1, and A can send something directly, and the total path cost will be 5. Let's put that into the table, and we can see that B is reachable at a cost of 1, and we can see that F is reachable at a cost of 5, and A will be the node on this path prior to delivering it to B and prior to delivering it to F. The candidates right now are indicated in green, so it's these neighbors B and F. Again, rather tiny font use there, but B and F are indicated as the candidates that are available. We have to select the cheaper of the two, 1 and 5. The cheaper is obviously 1, so we're going to select B. With B being selected, B is now a part of our known networks, and you can see that our cost will remain constant. It will never change, and A will do the final delivery. So the moment that we add a node to our set of known nodes, then we know that the path is fixed, and we know that the cost is fixed. Given that we've just added B, the next step is to consider the neighbors of B. And looking back at our earlier picture, the neighbors of B were A, F, and C. A is already in that set S. When we go back to the table just now, you can see that A is there. But what we can consider are the C and the F. And the C is reachable at a total cost of 2. F is reachable at a cost of 9. So going back to the table, you can see that C is reachable at a cost of 2, and it is this new node B that we've introduced that will do the final delivery. In the case of F, things are slightly more complex. The cost previously was 5, and you can see the convention that I used there. When I introduced the value, I underlined it, but then that remains an option, and I've copied that down. Looking at B that we've just introduced, we discovered that we can also deliver at a cost of 9. And there you can see A as the old knowledge and B as the new knowledge. Now clearly, if we have a situation where we are comparing 5 to 9, 9 is going to lose out, it's too expensive, and we can delete the 9 there, and we can delete the B there, and that gives us 5 and the A that remains in place. It's time to choose again. The candidates come in at 2 for C and 5 for F. C is clearly the cheaper option, so we are choosing C. At that moment that we've chosen C, the cost of C has become constant. It's not going to change in future while we work through this algorithm. And it's this new node B that entered the scene there that will do the delivery, and that is not going to change at all. Following the algorithm, we've just introduced C, so now we have to look at the neighbors of C. Looking back at the graph that we looked at earlier, there is C and the neighbors were B, D, and E. The only two things that are relevant is that if we use C as a basis, we can reach D at a total cost of 3, and we can reach E at a total cost of 5. In the graph, we've indicated it here. We can reach D at a total cost of 3, we can reach E at a total cost of 5, and for both D and E, it is the introduction of this new node C that enables us to reach those nodes at those costs. We are in the position again where we have to choose. We have 3 candidates available, D, E, and F. You can see the costs are 3, 5, and 5. The cheaper cost is obviously 3, so we are going to select the D. The moment that D is selected, you can see that the cost for D is fixed. It will remain 3 forever now, and the path to D is fixed. C will do the final delivery forever now. We've just introduced D, so we have to look at the neighbors of D to see what that offers us. Here we have D from our previous diagram, and we know that D can deliver to C, but that's useless because C is already in the set S. D can deliver to E at a cost of 5. Back to the table, you can see that we were able to reach E previously via C, but D now offers us a new opportunity. Previously, we were able to reach E at a cost of 5. The new possibility that is offered by D is also at a cost of 5. So it's not really a new opportunity. It's old news, and we can forget about that and simply keep the old value of 5 and the old prior node of C. It is time to select the cheaper of our 2 candidates. And here we run into the same problem that we ran into when we looked at this problem graphically. There is no cheaper one. They are both at exactly the same cost. As we noted when we looked at the graph, we can pick either of these 2. It doesn't matter. What we did there was to select F. So let's select F again for this example. And you can see F now appearing, and the moment that F appears, it means the cost to reach F remains constant forever. That will never change. And the node that will do the final delivery to F will remain A. That will never change. We've just introduced F as our new node that we know how to reach. So the algorithm says we should look at the neighborhood of F. This is what we looked at previously. And in this case, we could reach B and A, but they are known. So the only possible value we have in this is the fact that we can now reach E via F at a cost of 7. Going to the table, we can see that we were able to reach E at a cost of 5. So we've not even bothered to include this new fact because it's a useless fact. And the fact that F can deliver at 7 is also useless. We haven't even bothered with that. And we simply retained the old cost. It is time to choose again. We have to pick the cheapest candidate. There is only one candidate to be picked, and that is E at a cost of 5. So let's pick E, and once we've picked E, the cost of E will remain 5 forever, and C will do the final delivery. That is the result that we have to work with. In order to read this graph, we may ask the question, how do we, let's say, get to D? So what we do is we look up in the table who will deliver it to us if we want to go to D, and C will deliver it to us. Then the next question is, how do we get to C? And the answer is that B will deliver to C. And then the question is, how do we get to B? And according to the table, A will deliver to B. And the question that we are asking here, the bigger question is, how do we get from A to any given node? The given node in this example was D. So how do we get from A to D? There's the entire route, and you can see that we just traced it backwards. From D, we went to C. From C, we went to B. And from B, we went to A in terms of constructing the graph. And now we know what the route looks like. We could have included the costs as well, and the only thing that this adds is that if we want to go to D, it will cost us 3 units. So we know that that total cost comes in at 3 units. This was our rather quick journey through the Dijkstra algorithm. We used an example to illustrate how the Dijkstra algorithm works. And as was obvious, one just keeps applying the same steps, and by repeating it until all the nodes are included in the set of known reachable nodes, one can determine all the routes that originate at some given node. Hopefully, the video did become somewhat repetitive at some point, because it is when one encounters the repetition that one tends to learn, but we hopefully also use the repetition to encounter different situations that one may be faced with. There is also a video available that deals with the Bellman-Ford algorithm, and I invite you to look at that one if you have not yet done so.
Music on this